Hi class. In this video we're going to continue seeing examples of the Laplace transform, but this time we're going to start in the transform domain and go back into the time domain or the regular domain. So I'm just going to start with number 1 in this section. We have that the Laplace transform of some function is given by 4s plus 2, doesn't look like a 4, 4s plus 2 over s squared minus 2s minus 8. Now the key here is to do algebra, in this case partial fractions. So note that the bottom of this fraction factors. So we can hope to split it up as a over s plus 2 plus b over s minus 4. Now when we do this, we just find a common denominator here, and well, we find a common denominator to get equations which will solve for a and b, very similar to the method of undetermined coefficients here. So we're going to get as minus 4a plus bs plus 2b, and that's over this product now, s plus 2, s minus 4. And so we get the following. 4s plus 2 should equal, collecting terms into a polynomial in s, a plus bs plus negative 4a plus 2b. Writing this out, we should have, by again collecting the coefficients of powers of s, we should have 4 equals a plus b. And 2 equals negative 4a plus 2b. So as we covered in class, you can translate this into a matrix in order to use your calculator to help you. The corresponding matrix is, the corresponding matrix equation is this. Which yields a equals 1 and b equals 3. So what that means is that the Laplace transform of y of s can be written as 1 over s plus 2 plus 3 over s minus 4. And now both of these individually are on our chart on the right hand side, so we can easily move back to the left to get the function y of t. This should be e to the negative 2t plus 3 e to the 4t. And that's what we were looking for. So the key steps involved here are just algebra. Do partial fractions, set up your equations, and if you want, use technology to help you solve the system of equations. And now everything should be really close to being on your chart, so just use your chart to go backward. The next example I'm going to do is number 2. And it might look like I'm just going in order, and to some extent I am. But we're going to see a slightly different phenomenon here. Suppose that we have that the Laplace transform of y is e to the negative 2s times the quantity s squared plus 2 over s to the 4th plus s squared. Well, ideally we'd like to use partial fractions again, but we can't use partial fractions with the exponential. So we have to take what's in the box and just do partial fractions on that. So let's see. S squared plus 2 over, notice that this factors as s squared times s squared plus 1. So that when I do my partial fractions decomposition, get a generic linear over s squared plus another generic linear over s squared plus 1. And now again, I just find a common denominator here. And so just multiply these things out. You'll get as cubed plus bs squared plus as plus b. That looks like a 13. It's a b on board. And then multiplying the s squared through, we get cs cubed plus ds squared. And this is supposed to be equal to s squared plus 2. So I'm going to do a little simplification by collecting terms. I get a plus c s cubed plus b plus d s squared plus as plus b. This is still equal to s squared plus 2. So maybe I can split my work sort of in half. By equating the coefficients of s cubed, s squared, s, and the constant, we get, let's see, on the left-hand side, there are no s cubes. There's 1 s squared. There are 0 s's, and the constant is 2. The coefficient of s cubed on the right, however, is a plus c. And then for s squared is b plus d. And then for s is a. And for the constant is just b. And you may think, oh, it's a 4x4 system, so I should just automatically use my calculator to solve this. Except notice here, we have 2 of them solved for us. I'm reasonably sure that a is 0. Similarly, unless I've miscollected terms here, I think b should be 2. If a is 0 and I plug it in here, I get that c should be 0. And if I plug in b equals 2 into the second equation, I should get d equals -1. So what that tells me is that my Laplace transform is e to the -2s times, let's see, b is 2, so 2 over s squared minus 1 over s squared plus 1. Okay, well now I'm almost ready to find the inverse Laplace transform. I need to know what happens if I have an exponential in s. And what this leads to is a Heaviside function. And what we're going to use the rule with the arrow that goes from right to left. So from the s variables into the t variables or the x variables, whatever the regular variables that you're using are. So the easiest thing to do is to account for the exponential first via the Heaviside function. So we should get h of t minus 2. And whatever goes in the box here, the argument must match. So typically here we would get, if it were 1 over s squared, you would just get t. But since there's a 2, it's going to be 2t. But every t must be accompanied with a t minus 2. So we have our minus sign, and then 1 over s squared plus 1 is the transform of sine of t. So we have sine of t, except it has to be t minus 2, because that's what our rule tells us to do. One way to think about this is that the Heaviside function pollutes everything that it touches. The arguments have to be the same all the time. So this is it for number 2. Once again, we can see that it's partial fractions, and then we use our chart carefully. Okay, so the next example that I want to do is number 5. And here we have that the Laplace transform of y of s is 4s squared plus 2s plus 5 over s cubed plus 4s squared plus 5s. Okay, well, the same procedure is going to more or less work. We're going to need to factor the bottom. So we have 4s squared plus 2s plus 5 over s times s squared plus 4s plus 5. And at first it seems like we can factor this further, but I don't think we can. In fact, if I complete the square on this term, I get s plus 2 squared plus 1. So this has no real roots, which means we may as well just leave it like this for our partial fractions breakdown. So this should be a over s plus bs plus c over s squared plus 4s plus 5. In order to transform this thing, we're actually going to have to complete the square. But to get our coefficients a, b, and c, it's actually easier not to, because we'll just end up multiplying it right back out. So what we get is that 4s squared plus 2s plus 5 is equal to as squared plus 4as plus 5a plus bs squared plus cs. So this is a plus b s squared plus 4a plus cs plus 5a. And once again, comparing the coefficients of s squared, s, and the constant, we get a system of equations. On the left-hand side, the coefficients are 4, 2, and then 5. On the right-hand side, there are a plus b, 4a plus c, and 5a. And once again, we could use technology to help us solve this. That is to say, we could use our calculator by setting up a matrix equation, or we can notice that one of these equations is pretty easy to solve. In this case, it's the third one. If we know that a is 1, then we can easily find that b